All right, so this is lecture 30 on the last day. How cute is that? On the 30th day of May. Just a couple things to state. There will be an official announcement coming to Canvas. I don't know, probably over the weekend. But your final will be uploaded Wednesday of next week. So that's what, May 6th. And then it'll be due a week from that day. So 13th. And then all the details about everything will be on Canvas. So it'll be very much like the midterm. It's not going to be a time test per se. It's not, you don't have to log into any software. It's problems. You write up solutions and then scan it or upload it back, however, to Canvas so I can grade it. I know a few of you have emailed me about your grades. I will do my best to respond to those emails. You know, it's just, at this time, it's just really hard to do that. Keep up with emails, that is. So I'm not ignoring you. I'm trying to handle emails is in a priority that I think is correct. And so, you know, if you're emailing me about your grade and right now and you're in no reason, or you're not in jeopardy in any way, shape or means of failing, then, you know, right now that's excuse me, I'm congested. You know, but you know, if you absolutely need to know what your grade is on, you know, May 2nd, then keep emailing me. I promise I'll get back. I just, you know, I'm sifting through lots and lots of emails. Some other people, some of you are also emailing me about if something's missing, homework. Unless you hear from me, you're up to date. You know, I'm not gonna, let me put it this way. If you submitted like an old homework, like homework 4, and I didn't put it in the grade book yet, then just be confident that I have the grade for it. I just didn't upload it to Canvas yet. I haven't had a chance to upload all the grades to Canvas. It's just, it's one of those things that right now, I know you think it's important to you, and I get that, but my priorities, it's at the bottom. You know, it's updating those Canvas grades is time consuming for me because that's not an official grade book. So that means I have to take all my stuff and one by one plug it into Canvas. And it's, to be honest, it's tedious. So I will try to get that all completed before the weekend's over if I can, but I can't guarantee that. So if you're really, really concerned about your grade, the best thing I can tell you to do is just explode my email until I respond. I won't be mad, I promise. So
I just don't understand who's concerned about a C at the worst.
I don't know, but you know, some people, like, I don't know. One thing I've learned, I mean, I've been teaching for like 20 years, you know, this level. And one thing I've learned, and I think it has to do with how your middle schools and high schools do things now, is you guys are always worried about your friggin' grades. And I guess that's okay. I don't know. That's not the way it was for me when I was in school. It's not the way that when, you know, it's just, I guess because now when you're in school, everything's on the computer and your teachers upload your grades all the time. When I was in college, you didn't get a grade until 2 weeks after the semester ended, you know. It just was never something that crossed my mind. I would never email my professor and say, what's my grade? They would give us assignments and you know, that kind of stuff. But you know, And I'm not saying it's wrong that you're curious or concerned. Frankly, you know, it's not that I'm being lazy. It's just that I have lots and lots of things to do. And being that uploading your grades to Canvas isn't a job requirement, it's not anything that I am supposed to do. Now, if I do it, I mean, I'd like to do it. It's just that, you know, there's only so many hours in the day. And if it ever becomes where I have to do it, that's fine. And I'm aware that annoys some of you, because I'll get sort of, you know, some of your professors do upload your grades all the time, and then you love that, and then you complain about me. But you know, what am I going to do? And again, yeah, I mean, you know, hey, like I said, if you turn everything in, you're getting a C at minimum. So none of you, if you're worried that you've turned everything in, you can keep emailing me and asking. But unless I'll put it to you this way, and this is, I shouldn't say this on recording, but what the hell, I'll say it anyhow. It is hard to fail my class, even in the normal times. So I am not looking to fail anyone. The only people who get an F are the people that earn it because they don't do anything. If you give me at least a little bit of effort, you're not going to fail. In this semester, that means you're not going to get lower than a C. So anyhow, I don't know if that makes you feel better or worse. Well, hell, there's only like 6 or 7 you here. If you're actually listening, some of you just maybe taking a nap with your computer on. Yeah, I mean, I'm not looking to give anybody, you know, hurting grades. I'm trying to encourage you to learn and make the best of a pretty crappy semester. Okay, enough of that blabbering. We got a couple more topics we have to do before the end of the semester. And so we should probably do that now. So last class, we did a bunch of examples. I shouldn't say a bunch. I think we did like 4 or 5. We did the homework problems, really. And so I shouldn't say our last topic. I should say one of our last topics. It's more correct because our last topic was the binomial or the normal approximation. So last class we did examples about what was called mean sampling, or you know, we said we're going to take a portion of a population, we call that a sample, and we are going to compute its mean. And then we ask questions like, what is the probability the mean is equal to blah, or the probability the mean is greater than or less than some other number. And so a natural question arises if you're taking a sample, and it's the following. So suppose, I don't know, let's say, you know, let's try to tie it to one of our examples. To what we did before. So let's say, suppose we want to know about, I don't know, average credit card debt. We had a problem a few assignments ago about credit card debt for college students. So who knows why we're interested in this? We're interested in it. And the question is, how do we gain information about this? And once we gain our information, for example, let's imagine the following scenario. So suppose we randomly ask, 100 people. And compute this sample mean. All right, so then the next question would be, great. Well, what does it mean? So one way of analyzing or asking what it means is, question, how confident are we that this sample mean is representative of all people with debt? I mean, I tried to stoke this kind of thought in. Does that even make sense? I don't know. I tried to stimulate these ideas way back in the beginning of the semester. We came into class and I wrote these kinds of questions on the board, and I tried to stimulate ideas like, okay, well, where am I getting my 100 people from? Am I picking them from one area of the country? Am I picking them from one sort of age group? You would imagine that if I polled 100 people and asked them what their credit card debt was, and all of those people were under the age of 21, you would probably imagine that mean that you got is not representative of the population of all people who have debt. And that could be for many reasons. You might reason that older people have had more years to build up credit, and so they have more debt. Most people under the age of 21 probably don't have a mortgage or car payments or other types of debt. And so maybe their credit limit is not the same as someone who's 60 years old and has shown a history of paying bills. So there's lots of reasons that we would question our sample. So I hope this makes sense. If we're trying to gain information about a whole population by taking a sample, we have to understand that the statistics that we compute and the data that we analyze with a sample may or may not be representative of the actual population. So what we'd like to do is we'd like to develop ways to sort of quantify how quote unquote good or bad our sample data is. And so that's sort of where we want to go with our next topic. So notice how careful I am with my words. So one way to attempt to answer this is to use what we call confidence intervals. So a good way to think about what this is, just from a layman's viewpoint, is suppose, Liam, you go out and compute the debt of 100 people. Or excuse me, the mean of the debt. You go out and ask 100 people what their credit card debt is. You assume they're not lying to you. You compute the average. And then the next question I could say to you is, I'd say, okay, Liam, great. How confident are you that that number you computed, that mean, represents the population? You could say, I'm highly confident. I'm not confident. And since those are very vague in general terms, we'd like to change the language, and we'd like to use numbers to tell people how confident we are. And when we're studying things like numbers, one thing that's useful for us to visualize is a number line. And that suggests that using what we call confidence intervals might be something that's worthwhile. All right, so how do we set this kind of stuff up? So we kind of build it up in the following way. So let's go back to the debt example. So our sample mean, which we all know we denote it like this. So let's remember what this was. This was, say, mean 1 plus mean 2, or excuse me, not mean. These were the 100 values of debt that we collect, and then we divide by 100. So we give this a name. It's called a sample mean, but it's also wise to call it a point estimate. And to be very specific, let's call it a point estimate for mu. And remember what mu is. Mu is the actual average debt. Now, we don't know what that is. We're trying to figure out what it is. And so one way that we do this is we take a sample and we look for information that tells us that X bar is close to mu or it's not. Okay. So let's look at this from a math or a numbers standpoint. So let's put X bar and mu on a number line. Now we know every one of us has seen a number line before. Let's imagine this is 0, and then over here is X bar, and then over here is mu. Now, I haven't said, I've drawn it with a big gap, but that doesn't mean anything. There's no scale happening here. And so what I'd like to ask is, how far apart? Okay, so one of the things that you learn about in a baby algebra class is you learn about how to measure the distance or how far apart two numbers are. And the way we do that is we use what's called the absolute value. The absolute value tells us how far apart x bar and mu are. So let's write that down because sometimes it's worthwhile writing the actual mathematical formula. But if you try to answer this question, you run into a roadblock because the fact of the matter is we don't know what mu is. We are trying to get a good estimate for it. We're trying to determine what it should be, but we can't calculate mu in a practical way because, again, how could I possibly pull every single human being that has credit card debt? It's impossible. So the next best thing we do is we take a sample. We say, okay, I'm going to study 100 people, or I'm going to study 1,000 people, or I'm going to study 42 people. And when I study that sample, I'm going to get a mean because I can actually compute that. And what I'd like to know is that mean I get, is it actually close to what I would get if I actually could pull every single human with debt? Okay, so from what we know about the normal distribution, and by the way, I haven't said anything about how our sample we think it's distributed, but we do know that no matter what we study, no matter how it's distributed, the central limit theorem tells us for large values of n, the mean can be sort of thought of as being normally distributed. So theory tells us that if we want to study or analyze this x minus mu business, theory tells us that we could take a cue from the bell curve, the normal distribution. So let's make note of that. Get a different color. So even if we don't know how x1, x2, etc. are distributed, what does the central limit theorem tell us? The central limit theorem says x bar can be, and I don't want to say anything that's incorrect, so I'm not going to, get into the depths of this, but let's say we can study the mean using the normal distribution. Does anybody have a question or comment?
I'm confused because I'm like writing every single thing down.
Well, what? Okay, look, here's the thing, dude. You're gonna be confused. Uh, One of the things we have to learn about mathematics, statistics being a discipline under the math umbrella, and many other topics are this way too. But I think for particularly math and science, this is really sort of it comes, it just comes with the territory, and that is, you very rarely learn things the first time you see them. It's learning this stuff is not done in an hour lecture twice a week or an hour and a half lecture twice a week. Learning this stuff only happens if you take the time necessary outside of class, outside of the supplements. My role here, excuse me, my role here is to try to motivate some critical ideas. And again, I could come in here and just do, here's a type of examples you might be asked, but that's not learning. That's asking you to be like some poor robot to mimic me. And I just don't think that's the best way to learn. I think the best way to learn is to get some motivation, some ideas, and then struggle with how those ideas can help you solve problems. And that learning process comes with a steep curve often. Learning this stuff and actually learning it, not mimicking examples, but learning it. The learning curve for that is difficult. It's steep, I should say, for most humans. So one of the things I would encourage you to remind yourself when you're trying to learn this is that it's human to not get it right away. That's part of it. Very few people understand this the very first time they see it. What most students do, and I don't think this is the best way of going, but what most students do, especially those who even earn good grades, A's and stuff, is they don't really understand what they're doing. They just do enough practice that they've seen the examples and they can solve them. And that's not a bad thing. That's just, I think we train ourselves to do it that way because we're more concerned with passing tests than we are with understanding the material. Okay, so I don't know if that makes you feel better or not, Liam, but that would be my advice to you, is to remind.
Definitely got me thinking, but it doesn't make me feel
right.
better.
My point is if you want to learn this, it takes some effort, and it also takes some self-discipline to remind yourself that you're just not going to learn it overnight.
You're not alone.
What's that?
I say, Liam, you're not alone.
Yeah, no, but you have to remind yourself that.
Yes.
There's an issue with, and I've seen it mostly with math, and I don't know what it's like in other parts of the world, but it's clearly this way in the United States. Is there's this stigma that only certain people can learn math. And what we have in our schools is we've created this stereotype of what a math person is. And then when we don't do well in math, your parents buy into it and your teachers, and they say, well, you're not a math person, or you're a left-brained or right-brained, or whatever dumb stuff people make up to make us feel better.
Yes, that's universal. It's the same back home.
Yeah, and what's frustrating about that is that means that kids at an early age think the only people that can do math are the people who get it right away, or like those, the quote-unquote weird kids or the nerds who can do it in their head. But that's really not the case. What we need to understand is, yeah, there are some people who can get this quicker than others, just like there's some people who run faster than others. There's some people that jump higher than others. Some of you can sit down at a piano and play it without much thought. I can't do that. But guess what I've also never tried to do? Practice the damn piano. So if I say that I can't play the piano, that just means that I can't play the piano because I've never tried. I don't expect to sit down at a piano and get it the way Beethoven got it, unless I spend a hell of a lot of time doing it. And one of the things that I think happens with math especially is some people say, if I don't get it right away, then I just can't get it. Well, that's not true. But we're conditioned to sort of think that. It's unfortunate.
Well, I think that there's two factors to that. Mainly it starts like when you start learning multiplication, they're like, don't use your hands. And then it's like, don't try other methods.
Well, look, Liam, I can go on for days about how I think bad teachers and bad curriculum ruin it. Yeah, I get that. I mean, I couldn't imagine, you know, when I was a kid in school, that's how it was. You had, in math class was all about speed. Who can do it in their head? And all they would teach you these tricks and algorithms, but they never explained why they worked. And I guess years ago, that was more important because we didn't have technology to do the computation. But I think it's insane that a teacher would tell you have to solve a problem a certain way all the time. Now, it's also understandable that if I'm teaching you something, you know, I could say, well, I want you to do it this way on this time, and I want you to do it another way this time, and then on the third time, I don't care how you do it. You do it your way as long as it works. I mean, I think that's fair. But yeah, to tell someone they have to do certain things a certain way. Well, hey, look, you guys watch sports, you listen to music, you do all things in life. You guys learn in life. There's some people that are good at it. There's some people that aren't good at it. Guess what? That's no different in teaching. Some of you had good fifth grade math teachers. Some of you had shitty fifth grade math teachers. Some of them encouraged you. Some of them probably didn't. Who knows what the whole story is. And so that's just the luck of the draw. That's unfortunate. And also some of us are biased. I may have liked all my math teachers because I happened to be better at it than I was at other things. It came easier to me. But it doesn't all come easier to me. It's not like my whole life I got straight A's in math class. No, I mean, eventually we get to a point when we're trying to learn any subject where it becomes difficult. And that's where you have to find something that makes us want to learn it. And that's hard. I mean, especially right now, think of it. Some of you are trapped in your house or wherever the hell you're at. Who knows? Apartments, living with roommates or family. You know, I couldn't imagine if I was in college and this happened and I had to go home and live with my parents. I'd probably take a bridge. So I don't know what kind of situation most of you are in, or some of you, or who knows. Maybe you guys are all loving life right now. I have no idea, but I can't imagine this is the best time to want to go out of your way to learn stuff that you're not that interested in. I mean, how many people are taking this class because they want to learn about it? Most people don't. You're taking it because someone's saying you have to. And no matter how I tell you it could be useful, you don't give a crap. You just want to get through it. And I don't necessarily blame you, especially right now, but it's hard to motivate yourself to learn difficult things if you're not interested in them. You know, I don't want to sit around and analyze Shakespeare or analyze philosophers from 300 years ago. That just doesn't interest me right now. But I did have to do it once when I was in school. All right. Yeah. So look, we can all agree to disagree on some of this stuff.
Yeah.
But, you know, look, I'm trying to make the best of it here too. I don't know. Maybe you guys don't like what we're doing here. I don't know. But I figured doing this is better. It's me giving a better effort than just saying read these things or watch these videos and then go do problems. So
teachers like that.
Well, I don't know. Maybe there are. And I don't know. Some people might like that. Some students may like the online way of doing things. I don't know. I know myself I wouldn't. I like the interaction. But everybody's different. We have our own sort of ways of doing things. All right. So let's get back to this so we can get to examples. Hey, look here. Let me transition to talking about crappy teaching. So most people who teach this class, in most textbooks at this level, would literally not say anything about the central limit theorem. They would say, today we're going to talk about confidence intervals, and then they're going to throw these crazy ass formulas in front of you, with no motivation whatsoever from where in the hell these formulas come from. And I just think that is a cop-out, crappy way of teaching, and it's not helping you guys learn new ideas. It's making you think you have to memorize silly-ass formulas. I don't want you to have to memorize silly-ass formulas. I want you to understand that these scary formulas have a reason where they come from, and then remember that you can look them up at any time you want to. You know, are there still people making you memorize things? I always laugh, and if any of you do this, I feel bad. But I one of the things I laugh most about was when I'm walking like down the halls, and I see you studying in the library, and you have flashcards, and I just think that, and this might sound terrible, but memorizing things from flashcards to me seems to be one of the stupidest things I've ever seen. Now you might say, "F you, O'Grady, it works for me," and that's fine. But I just think there's got to be there's got to be many better, more efficient ways of learning than reciting words and memorizing definitions. Like, you know, I just think the mind doesn't work that way, but we think it does. Anyhow,
it doesn't. The second you have the test, you forget everything.
Yeah, I mean, I hate to use the word stupid. My kid's probably upstairs like, my dad's saying stupid. I'm not allowed to say stupid, but I really hate the word. I just think it's bad. I don't think it's learning. I think you're just training your brain to do something that you're going to forget, because it's not muscle memory. It's not like you're doing something over and over again so that it becomes habit. You know, I use that silly story all the time. When you get in your car and drive, you don't have your driver's manual sitting next to you and say, "Oh boy, here's a red light. What do I do?" Right? You don't do that. You know what to do because you've done it over and over and over again. Well, I hope you know what to do. Some of you don't, and then you wreck, and then that makes my insurance premiums go up. And then I get mad because then it comes full circle that you didn't understand the damn probability, and now my insurance premiums are. All right, but I digress. So anyhow, what I'm going to write here is trying to convince you, or trying to give you some intuition. Maybe that's a bad word. We're trying to show you where these scary formulas we're going to write down in a second, where they come from. All right, so if I draw a curve, which is the bell curve, let's see if I can draw it pretty on the first time with, at least, I shouldn't say pretty, but make it look realistic. So remember, the bell curve looks something like this. Well, actually, let me be very careful with this, because I don't want you to think this is a bad thing of doing this. That's not necessarily the y-axis. So let's put. Let me get a different color. Use pink. I like a good pink. So this is not the y-axis necessarily. It could be, but it doesn't have to be. What this is this is the mean, this theoretical population mean, mu, that we're trying to figure this out. We want to know what the average credit card debt is. That's what we're trying to figure out. And here's what we know about this scary function called the normal distribution and its graph. Is we know that this thing is this bell curve. It's symmetric, and what's interesting about it is we have these numbers that are very useful to us. So let me get my pink back. For example, we know that this point is mu plus a standard deviation, and then the symmetric guy to the left would be mu minus a standard deviation. Ah, that's ugly. Let me rewrite that in case you actually care. I do feel bad for some of you, because you're probably, if you do watch this, which I don't even know if anybody does, I go through all this trouble to put them on the internet. Who knows if anybody watches them? But some of you are like, I care. Why does he always say we don't care?
Force of habit.
Yeah. Okay, so what we know is we know that so much of the area under the curve is between the first standard deviation, and here's probably the most important one, is this mu plus 2 standard deviations. So let's put that one here. And so the key to understanding what I'm going to say is that if you look at the area, let me get a different color. Let's get green. I don't know. Let's use yellow. So let's take this. So what I want you to sort of see, so I'm going to try to shade. This ain't working either. I'm going to have to go to school to learn how to use this applet so that I can make better pictures for you guys. What I'm trying to do is shade this area under the curve in. So let's get red out. So 95% of the area under the curve is between mu minus 2 standard deviations and mu plus 2 standard deviations. Now, what I'm saying is we're not counting what happens outside of that. We're saying all the area under the curve is 100% of the area. And 95% of it, and that seems intuitive looking at the picture, we're leaving out those little tail pieces. Ooh, that's where we're at right now, actually. If you listen to some of the risk analysts with the pandemic, we're in the tail risk. But 95% of the total area is between mu minus 2 standard deviations and u plus 2 standard deviations. And if we write that in what we call interval notation, you guys might remember this sort of stuff. We could say in an interval notation, this is mu minus 2 sigma comma mu plus 2 sigma. Okay, now, what does this mean? What does this picture mean? What does this have to do anything with this, excuse me, this confidence that I've been talking about? And I apologize for keeps clearing my throat. I feel like I'm annoying you, but whatever. Okay. Now, we have to understand two things. This is the normal distribution. Now, the big theory, the law of large numbers and the central limit theorem tells us that even if the x1, x2s aren't normally distributed, that the mean is distributed normally with a certain standard deviation. So what does the picture on the previous page means? Well, it means the following. So this means 95% of sample means from a large population will be between mu minus. Now, we're not going to write, well, let's write it first like this. Now, let's be very, very careful with this. I don't want to use sigma. I'm using it in two contexts, and this is confusing. So let's remind you that we have to put the square root of n here. Now, this formula is not 100% correct. Because we have this 2 here. So what do we do to make this correct? Well, we have to remember a few things. So if I go back to the previous slide, if I compute my sample mean, we know that the sample mean is quote unquote normally distributed. That's by the central limit there. And we know that there's a 95% chance it falls between 2 standard deviations of the mean. Now the problem is the mean, or the standard deviation I'm using here on this slide is the standard deviation that comes attached to that exponential function, the normal distribution. We wrote that down a while back. It's scary, but its graph is this creature here. Now, let's be a little more specific. Because again, we're glaring over the details. So let me actually say this a little more, let me say it a little more accurately. Because perhaps what I'm going to write next will not seem, it'll seem like I'm doing magic. So let's not use the word will. Let's use the word should. So it turns out after doing math, which I'm not going to make you go through, it's actually the following. It's actually the following values. So what we wrote in the black above would be technically correct. Well, if I didn't put that square root of n in there, if I just had the sigmas, that would seem to be correct for a normal distribution, but that would only be with a normal distribution of mu, mean mu, and standard deviation sigma over n, but that's not exactly what we have. What we actually have is we have this. We have 1.96. It's not the actual value 2, it's actually 1.96. Now, again, if you want to know why that's actually the case, it requires some more math. Calculus is the first step you need. Okay, so this is one of the key observations that we need. So here's some more terminology. If you have a question, please stop me, by the way. So what we do is we call this creature 1.96 sigma over square root of n, the margin of error. Now, if you go to the previous slide, we have a much better way of writing this inequality. So when you're in an algebra class, you learned about inequalities and how it can be rewritten just by doing algebra. You can add or subtract pieces to multiple sides. And so what we're really, one way of writing this is that the distance between our sample mean x bar and the population mean mu is always less than or equal to 1.96 times sigma over n. Or we can write as, now I write it the other way. If I expand it back out, or if I take the previous page's inequality and I rewrite it, I can write it so that I get information about mu. I guess I should, you know. So this right here is called, the name for this interval is the 95% confidence interval. Why are we calling it that? We're calling it that because we are 95% confident that our sample mean is within this distance, or it's this close to the actual mean if we could theoretically calculate it. Okay, so this is, again, this is my Zoom sitting in my basement while kids are laughing and playing upstairs with Amy attempt to explain a very complicated math concept in a way that hopefully you can make sense of without knowing calculus and higher math. I'm not saying this is easy to learn, and perhaps, you know, you just give up, and I'm not going to fault you for that. But at least, you know, I give it my attempt. If you want to learn the details, there's this great book, which I will recommend right now. This is where I learned it from. It's called John Froome's Mathematical Statistics. And then you can get, and by the way, this is a class you would take if you were a math major, and after, in your like junior year, maybe sophomore year. And you wouldn't even get to learn about this until, I think, what is it, chapter 13, I think, 12? No, chapter 11. Estimations of means. Yay. All right. Look, there it is. Confidence intervals. Good stuff. Does anybody have a question? Going once. Like I said. Now, we don't always have to do 95% confidence. We can do other confidence levels. We can do 90. We can do 99. So at this time, it's interesting. Unfortunately, if we were in a class right now, it'd be nice because I could actually pull out the computer and simulate a bunch of data to give you maybe a feel for why all this works. But we just can't do that right now. Although I guess I could have. Okay, so let's do an example. And then we'll call it a day, and then we'll give you examples just like this example, and you can ask about them if you don't understand them on Tuesday. Does anybody have a question? Comment, concern? All right. So let's suppose you sell something. I don't know. What can we sell? Let's get something realistic. So here we go. We are interested in understanding how long a pair of headphones sits on a shelf before being sold. So a random sample of 75 headphones has, say, a mean of 62 days. So the idea is if we take 75 headphones and we track how long they sit on the shelf before being sold, we compute that mean, we get 62. Okay, so now we can't answer this question with just this information. We have to make some assumptions. So one of the assumptions, if we don't know it, is we take a good guess at what we think maybe the standard deviation would be. So assume the standard deviation. Now let's be very careful. You might say, why would you assume? Can't you compute it? Well, I'm not assuming the sample standard deviation. I have to assume the population. So let's say that's 5 days. So what we want to do now is we want to analyze the population mean using our formula. So we have information. We have our random sample. We know what n is. It's 75. We have our x bar. Our x bar is 62. And then we're making the assumption that sigma, the population standard deviation, is 5. So let's analyze the population mean. So what we're going to do is we're going to analyze. Using our confidence interval. So what was that? Well, that was mu less than. By the way, you guys, we know that maybe we should stick to just less than, just to be safe. But we talked about how when we're computing probabilities of continuous distributions, it doesn't matter. Well, I shouldn't say it doesn't matter, but I'm not getting into the details of that. Doesn't matter for us. How's that sound? So we know that this formula is the one that could give us information. And so if we plug in all this stuff, what was our mean? Our mean was 62, I think. Yeah, 62. Our sigma was 5. Our n was 75. So now we can just compute these values. So let's not waste too much time because we've already, if not bored you to death, scared you to death with everything today. So if I go to a calculator, what is it? 62 minus 1.96. Whoa. Give me 1 second because it's not working. Who turns their num lock off? My kids must have went to town on this. All right, so what you end up getting is you get that this is 60.86. I guess technically, all the data we gave were whole numbers, so I guess we should round up just one decimal place. So let's say this is 60. Okay, so we'll be 60.86. We'll do 3 decimal places right now. And there's lots of conventions on how you should round. I'm not real concerned with that in this class, but some people are, depending on what they're doing and their opinion on it.
Where did we get 5?
What's that?
Where did we get the 5 from?
5 is if you go back to the very last line, it's the standard deviation of the population. That's what we're assuming. Does that make sense?
Yeah, that's good. Thank you.
Yep. Now, of course, you might have the natural question, well, you might say something, and it's a great question. These are things for you to think about. You might say, well, how can I know the standard deviation of the population if I don't know the mean? So these are great questions. And these are ones that, obviously we can analyze more if we had more time and more math, but, you might say, and it's a perfectly natural question. I remember when I took a class like this many years ago, one of the students said, well, how in the world can we, so what these problems are basically doing is they're allowing you to study the mean, assuming you know something about the standard deviation. But you might say, well, heck, O'Grady, all those formulas about standard deviation relied on the mean. So it's almost like weird logic or circular reasoning. And those are great questions. And notice we're being very careful with our words by saying assume and stuff like this. There's a time and place to learn of the more specifics. So just keep that in mind. It's always good to be asking questions to yourself and doubting these things. Okay, so what does this mean? At least what the theory tells us. Just because the theory tells us it doesn't mean it's the way it works, but here we go. So here's the conclusion. Moral. We can be 95% confident the population mean satisfies, we'll call this star. Now, imagine, put this in a real world scenario. These are things that like Amazon would love to study when they're, anybody who manufactures and or ships and sells products. How long do we expect things to stay on the shelf? You don't want to have a warehouse too full. You don't want to have a warehouse too empty. You don't want to have store shelves too full. You don't want to have store shelves too empty. I mean, think about what happened a little over a month ago when all this coronavirus stuff hit, and then you go to the grocery store and shelves are empty. There's no meat. There's no toilet paper. Anyhow, not getting too off topic, but does anybody have a question about this? Okay, so what we'll do is we'll end it here. We'll give you some practice problems to do, and then we'll also talk about some of those questions I alluded to, like, is this real world? And how can we estimate the mean using known information about the standard deviation? How would we know information about the standard deviation? Okay, so do you guys have any questions? All right, well, hopefully you guys are intrigued to try to learn something more. And then I'll post an assignment later today. Have a great weekend, be safe, and I will talk to you guys next week, hopefully. Take care.